A few other ways that our understanding of equilibrium can help us in understanding solubility at a deeper level. So the first thing I want to talk about is how solubility changes in different solvents. So yesterday we learned how to calculate the solubility of a substance in pure water. Today we're going to look at what happens if a substance is dissolved in an aqueous solution of something instead. So the example we're going to be using is BZ2 from yesterday, so the same KSP, same solubility that we calculated. So in the last video we calculated the solubility of BZ2 in pure water to be 1.8 times 10 to the minus 4th molar. So that again is the maximum concentration that can exist in solution when pure water is used as the solvent, or the concentration of a saturated solution. So this is asking us, how would its solubility change if it was dissolved in a 0.1 molar solution of Mz instead of water? So we can answer this question two different ways, depending on exactly how it's phrased. I intentionally left this one ambiguous so we could discuss kind of both sides of the story here. So we can answer this either qualitatively or quantitatively. So first up, let's take the qualitative side of things. So qualitatively, we can use Le Chatelier's principle to think about this. So when we're dealing with solubility equilibria, solid here, we're always dealing with the solid becoming its aqueous ions. So here, that is solid BZ2 becoming 2Z minus and, B2 plus and 2Z minus. So if we think about what's happening here, in yesterday's scenario, when we dissolved this in pure water, we had concentrations of 0 of both of these things before anything was dissolved. But now, we still have no B, but there's already some Z ions present in solution. So this concentration is not 0 to start, it is 0.1 molar. So if we think about what that means in terms of Le Chatelier's principle, there's already 0.1 molar Z in solution. Before any BZ2 actually dissolves. So we've essentially introduced more product into our system to start with. Before we even let this reaction start, we're putting some product in there. So we're adding product to this system compared to pure water. So water doesn't have that presence of Z ions there initially, and this solution does. So adding product, according to Le Chatelier's principle, is going to cause our reaction to shift to the left, or in this case, it hasn't had a chance to start yet, so it's just going to stay further to the left. So this causes our equilibrium to stay further to the left, and the left side is the solid here. For equilibrium is staying on the left side, that left side is our solid. That means not as much is going to dissolve. So left in a solubility scenario means solid. If more stuff is staying solid, less of it is going to dissolve. So less stuff dissolves when we have this ion already present. So this is known as the common ion effect. But it's really just an extension of Le Chatelier's principle, which we already know about. So the common ion effect says that the solubility of an ionic compound will be lower when a common ion is present in solution. But again, this is just using ideas that we already know. Really, all of solubility equilibria is stuff we already know, just with new labels on it for this one specific context. So you will always find that when a common ion, when one of the ions in your ionic compound is already present in solution, the solubility of your compound is going to be decreased. So we can explain this qualitatively through the Le Chatelier's principle, but we can also quantify this. So from a quantitative standpoint, we can actually calculate what our new solubility is going to be. So we can set up an ice table, very similar to what we did yesterday. BZ2 is a solid, so we can ignore that. The only difference is that now our I row is representing our 0.1 molar MZ solution. So yesterday it was water. It's always whatever your solvent is. Yesterday that was water. Today it's a 0.1 molar solution of MZ. So the only difference is going to be what are our initial concentrations. In water, everything is 0. Here, we still don't have any B present, but we're starting off before any BZ2 dissolves with 0.1 molar Z already present. From here, it's exactly the same. So you will finish up setting up your ice table, write your KSP expression, solve for X. X is your solubility. So try to pause the video here and take a couple minutes and do that. It's from here, it's exactly like we did yesterday, solving for X. And now let's work through this together. So finishing off our ice table, we still have 0 of one of our products, so we know that our concentrations are going to increase as we reach equilibrium. A little bit will still dissolve. So at equilibrium, our concentration of B will be X, our concentration of Z will be 0.1 plus 2X. So then, our KSP expression is exactly the same as the one we used yesterday. The concentration of B times Z squared, so we can plug in everything we know. We were given the value of KSP as 2.4 times 10 to the minus 11th. From our ice table, the concentration of B is equal to X. The concentration of Z is 0.1 plus 2X, and that's going to be squared. So now, just like we've done in other ice tables, because K is very small, we know that X is very small. So to simplify our life, we can ignore added and subtracted X's. So 2.4 times 10 to the minus 11th is approximately equal to X times 0.1 squared, or 0.01 times X is 2.4 times 10 to the minus 11th. So that means that X, which is our solubility, is 2.4 times 10 to the negative ninth. So this is our solubility. So yesterday we found it to be 1.8 times 10 to the minus fourth, having that 0.1 molar concentration of Z present already in our solution decreased our solubility by 5 orders of magnitude. So that's a pretty big effect for not a very big concentration being present initially. So this is something that you should be able to calculate. Again, the only real difference is what is your initial concentration, and then that affects the rest of your calculations from there. But that's the only thing in here that actually changes. So the other thing that I wanted to talk about today is using equilibrium principles to actually predict if a precipitate will form or not. So we've used the solubility rules, but the solubility rules are more guidelines than actual rules. Something that is insoluble does not always precipitate. But we can use our understanding of equilibrium to predict exactly when it will and when it won't. So I want to talk a little bit about this idea of predicting precipitation. With equilibrium principles. So precipitation, we know, is the reverse of dissolving. So the reactions that we've been talking about with solids becoming aqueous ions, when that runs in reverse, that is precipitation. So we know a precipitate forms when we usually say a precipitate forms when something is insoluble, but that's not quite true. A precipitate forms when the concentration of your dissolved ions is greater than that of a saturated solution. So a saturated solution is the highest concentration we can have under normal circumstances. When your concentration is higher than that is actually the only time a precipitate forms. So you can have an insoluble substance present at a very low concentration and it'll stay dissolved as long as its concentration is lower than whatever is saturated for that substance at that temperature. So remember also that saturated for these systems is the same thing as at equilibrium. So if we have a saturated solution, we have the system at equilibrium, so all of the concentrations that we've been calculating in these videos so far have been for our system at equilibrium. If I just mix a random amount of stuff together, I don't necessarily know whether it's at equilibrium or not, but I can calculate that using Q, using the reaction quotient, just like we've done for all sorts of different equilibrium systems. So precipitation occurs when a reaction is too far to the right, is to the right of equilibrium, and it needs to run in reverse. Precipitation occurs when Q is greater than K. Because that is when our reaction runs in reverse. So if you actually want to know whether or not a precipitate is going to form from a quantitative standpoint, use the concentrations of ions in your solution, and the equilibrium expression for the solubility reaction If you find that Q is greater than KSP, your reaction is going to go backwards. If you find that Q is equal to KSP, it's a saturated solution. If you find that Q is less than KSP, it's an unsaturated solution, and you could actually dissolve more.